Introduction to Transformations, Sketching Basic Graphs. What we're going to do today is look at 6 basic graphs that you will need to be able to draw quickly using key points and the features that you are familiar with. What we're going to do for each of the given equations is sketch the graph with a table of values, and then we're going to identify some things like the domain and range of the graph, the equation of any asymptotes if there are any. We'll also determine if the relation is actually a function, if it is a one-to-one function, or neither. Let's go over the first graph and use that as an example to find all of these features. For a linear graph, we are hopefully already familiar with the pattern, so you can go ahead and fill in your linear graph. We notice the graph keeps going in both directions, so our domain of this graph is all real numbers. Writing this in set notation, we use the set bracket and we write x such that x is an element of all real numbers. Now we'll do the range. The range is also all real numbers, and we use the variable y, otherwise it looks very similar. We start a set bracket, y, such that y is an element of all real numbers. Now to decide if the graph is a function, it needs to pass the vertical line test. I'm going to highlight a line for this just to make it a little bit clearer. If you draw a vertical line at any place along the graph, you'll notice it only crosses the relation at one point. For any x value, there should only be one y value. That is what makes something a function. So we already know that y equals x is a function by the vertical line test. In order to decide if it is a one-to-one function, it also means that for any particular y value, there can only be one x value. We check this with a horizontal line. If the graph also passes the horizontal line test, we know it is a one-to-one function, like this first one. One-to-one function. If a graph passes the vertical line test only, it is still a function, it's just not a one-to-one function. Let's take a look at the second one, the quadratic, which hopefully you also remember how to graph, but if not, let's fill it in. For the quadratic graph, aside from starting at the vertex of 0, 0, we can use a table of values, or we can remember our easy pattern. It goes across 1, then up 1, across 1, up 3, and then you can keep following the pattern across 1, up 5, across 1, up 7. In order to get more points to graph quickly. So we don't need a table of values every time if we know how to start at the vertex. All right, domain for this graph, still all real numbers. X such that x is an element of all real numbers. But we do have a different range for this graph. So to check our range, what values of y do you see on the graph? We have a minimum, and that minimum happens at 0, so we know that y is greater than or equal to 0. In set notation, we write y such that y is greater than or equal to 0, and y is still an element of all real numbers. Now it's up to you to decide, is this a function, a one-to-one function, or neither? Let's apply our tests. The vertical line test, wherever you put a vertical line at any place in the graph, will only cross the graph at one place, so it is a function. However, if we try the horizontal line test, you'll notice there are multiple places on the graph where if you draw a horizontal line, a particular y value has different x values. We can even see that in our table of values. If we consider the y value 4, there are 2 different x values that have the same y value. In this case, the graph is still a function, but it is not a one-to-one function, so we would just call it a function. Okay, on to the third. The third is a cubic, which you may or may not remember graphing, but we're just going to do so with a table of values. And you'll notice this graph grows very quickly. If we try to get another point on there, it is going to be way off the graph, but the idea is if you know these 5 key points, that's enough to get the basic shape of the graph. All right, looking at our end behavior, we can see that we still have a domain of all real numbers. So we'll write x such that x is an element of all real numbers. And again, the graph keeps going up here, it keeps going down here. So we know between those two that our range is also all real numbers. So y such that y is an element of all real numbers. Okay, using our vertical line test, wherever we place a vertical line, it is only going through one point. It also passes our horizontal line test, meaning for any y value, there is only one x value. So we can say this is a one-to-one function. All right, once you've got those three drawn, let's go on to some slightly more interesting graphs. Okay, our fourth type of graph is the absolute value function. As a little reminder, if you don't remember what the absolute value function does, these bars tell us to take the positive value inside, and we can treat those absolute value bars as a specialized kind of bracket. So it affects order of operations, and then your result inside the bracket is also positive. So for example, the absolute value of -2 is just 2. Absolute value of -1 is 1. And then we go 0, 1, 2. So it always gives you a non-negative value. Using that to graph, we can see we do follow a linear pattern with our positive numbers, and we can even extend it a little bit. However, whenever we have a negative x value, it is going to give us a positive or reflected y value. So we kind of have two pieces of linear functions. Or you can think of it as one linear function where half of the function with the negative x values has been reflected. Sorry, let's fix that line a little. And we get this kind of V shape. Again, the pattern for this one is pretty easy. You just need to know where to start your graph and then follow the pattern. All right, let's quickly fill in domain x such that x is an element of all real numbers. Range. We can see we do have a minimum on this graph. So we're going to say y such that y is greater than or equal to 0, and y is an element of all real numbers. The graph does pass a vertical line test, but we can see there are several places where it does not pass a horizontal line test. I realize there are some places where it could pass, but as soon as there is one place where it does not pass, it is not a one-to-one function. So it is a function, but it is not a one-to-one function. All right, the next one, reciprocal function. Not sure why the word function is all the way over there. It is a reciprocal function. Now this function is the function of 1 divided by x, which creates a little bit of a restriction on x. Take a minute to think about what that restriction could be. Pause the video if you need to. So our restriction comes from the fact that we are dividing by x and we cannot divide by 0. So our restriction is that x cannot be equal to 0. Let's fill in the rest of the table of values first, and then we'll look at what that would look like on a graph. So for this table of values, I did the same x values as before, but that's not really enough information to figure out the shape of the graph. So we're going to add in a couple extra points. Now let's start with sketching the values for -2, -1, 0, 1, 2. So if our x value is -2, our y value is -1/2, and we're going to have to approximate that, but just try and get it halfway. We have a point at -1, -1. We cannot have a point when x is 0 because that was our restriction. You'll notice I left that blank. That can actually be taken off your table of values. We don't want it. Okay, and then we had a point at 1, 1 and 2, 1/2, and you can see that is not enough to get the shape of the graph. With our two additional points, with an x value of -1/2, and we are going to have to approximate that, we get a y value of -2. With an x value of +1/2, we get a y value of 2. Now, because we're dividing by x, having a small x value will give you a larger y value. If we need a couple more points just to kind of try and figure this out, imagine, let's say x had been 1/4. When you do 1 divided by 1/4, you get 4. So we also get a point up here at 4. You could do the same thing with -1/4 and get a point at -4, and that would give you a point down here. Once you kind of start experimenting with those other points, that's enough for you to sort of see the shape of the graph, which is a curved line that gets really close to the x and y axis, but does not touch them. And let's draw that in first, and then we'll think about why that is. So curved, approaching, sorry, it shouldn't be curving away, curved and approaching the axis, curved and approaching the axis, but not touching the axis. Now the reason it doesn't touch is because of that restriction. So we say that x cannot be equal to 0. That means there is no place on the graph where x can be equal to 0. The way we draw that on the graph is by doing a dashed line called an asymptote. I'm going to highlight my dashed line just to make it a little easier to see, but we would draw a dashed line just going along the y-axis where x is equal to 0. We can call that line x equals 0, and we can call that line a vertical asymptote. Vertical asymptote. So usually if I was labeling this, I would say we have a vertical asymptote at x equals 0. Now you'll probably notice by looking at the graph that we did something similar here. The reason for this is come back to our original equation. If we look at this entire equation, is there an x value that could give you a y value of 0? Is it possible to have an x value 1 divided by something so that y will be equal to 0? We can see that's not actually possible. And the way that's shown on the graph is with a horizontal asymptote. So we call this one a horizontal asymptote. At y equals 0, the horizontal line where y is equal to 0. Now, this graph is a little trickier to remember how to draw, so you want to get yourself really familiar with the key points and just be able to remember approximately what the shape looks like. Finding these points up to there is usually enough to sort of remind you of how to draw it. All right, domain and range. Now this one, we do have a little bit of a limit on your domain and range because we said that x cannot be equal to 0. And also we know that y will not be equal to 0. So our domain is x such that x is not equal to 0, but x can really be anything else. Similarly with our range, y such that y is not equal to 0, and aside from that, y is an element of all real numbers. Now, looking at the graph, I'm actually going to just fix my asymptotes a little to make it easier to do our vertical and horizontal line test. So I will redraw those asymptotes in just with like a dashed line to the best of our ability. I know it's not going to be as visible when it's on the x and y axis, but there we go. And now let's go back and do our vertical line test. Now, in a place like this, it's very clear that your vertical line is only crossing the graph in one place. Keep in mind that even when we have a line over here and that line gets very steep, all of those values are slightly different. So at any point when you have a proper thin line, it is actually only crossing at one place. So it does pass both the vertical line test and the horizontal line test wherever you test the line. That means this is actually a one-to-one function. And that's probably the trickiest function we're going to graph at the moment anyways. All right, on to our last one. Our last one is the square root function. A little bit easier. Let's get rid of those extra points. All right, now we do have a restriction on our square root function, so we need to remind ourselves what kind of restrictions do we have if we are taking a square root of x. We cannot take a square root of a negative number, so x must be greater than or equal to 0. It's fine to take a square root of 0, just not a negative number. Now if we start with 0, 1, and 2 for our x values, you'll notice we're not going to get very far on the graph. Because we're taking a square root, I picked some convenient values that are easy to take a square root of, like 4 and 9. So usually when I'm graphing this, I probably wouldn't even bother with that point there because it's a little bit of an awkward point. But if we want to know approximately where it is, the square root of 2 is approximately 1.4, just to give you an idea of where it goes on the graph. So we have a point at 0, 0, 1, 1, 2, and then 1.4, which we're definitely approximating, 4 and 2, and then 9 and 3. And we get a curved shape. You'll notice that it actually looks like half of a parabola turned sideways, and that's exactly what it is actually. It is the inverse of our quadratic function y equals x squared. However, because we only have a positive square root, we only end up with half of a parabola when we turn it on its side. If we had a negative sign in front, we'll come to this later, but if we had a negative sign in front, you would get a reflected graph down here, which would give you the other half of the graph. But when we just do the positive square root, it's just going to be that positive part right there. Okay, a pretty easy one to draw, just need to remember that restriction. So our domain for this, because we have a restriction, is that x must be greater than or equal to 0. And as a result, if we look at our graph, we also don't end up with any negative y values because x is always greater than or equal to 0, so is y. So our range is y such that y is greater than or equal to 0. And now we decide what kind of a function it is. So clearly it passes a vertical line test, and it also passes a horizontal line test. For any x value, there is only one y value. For any y value, there is only one x value. This means it is a one-to-one function. All right, that is our 6 graphs. What you want to be able to take away from this is you want to remember what all 6 of these basic graphs look like, and you need to be able to quickly sketch them using their key points and use that to identify things like domain, range, and decide if it's a function, and if so, if it's a one-to-one function. That's all for now.